All right, so let's talk about hydrogen bonding. I mentioned this earlier when we talked about H2O, H2S, and there was an anomaly in our predictions. And then that anomaly, okay, is due to what we call hydrogen bonding. Okay, this hydrogen bonding is an interaction that occurs between two molecules. One molecule has a hydrogen that's attached to one of the three most electronegative atoms. The three most electronegative atoms are fluorine, oxygen, and nitrogen. Okay, so these are the most electronegative atoms. So anytime you have a hydrogen, here's a hydrogen attached to an oxygen. This one right here is a very polar bond. So anytime hydrogen is attached to fluorine, oxygen, or nitrogen, the bond is very polar. So there's a very highly positive, partial positive charge on the hydrogen. So it's almost bare of electrons. The electrons are almost all the way to the other side, to the oxygen, the fluorine, and the nitrogen. So that makes it very attractive to a neighboring molecule that has a lone pair of electrons. So if you have another molecule nearby, and it has an oxygen, a nitrogen, or a fluorine, like a water molecule nearby, that molecule nearby, the lone pair in that is going to be strongly attracted to that hydrogen. That interaction is called hydrogen bonding interaction. That's a little bit, that's significantly more significantly stronger than your London dispersion forces. So that explains the anomaly between H2O and H2S. You would have expected H2S to have stronger attractions based solely on the size of the molecule, London dispersion forces. But water molecules have these additional attractions for each other resulting from hydrogen bonding interaction. Okay? Okay. So let's look at this question right here. How many atoms in the acetic acid molecules shown here are capable of hydrogen bonding interaction with water molecules? So if there was a water molecule nearby, okay, what type of atom is capable of hydrogen bonding interaction? A hydrogen that's attached to fluorine, oxygen, or nitrogen. Do you have any hydrogens here that's attached to fluorine, oxygen, or nitrogen? Which one? This one, right? This is oxygen. This is oxygen, that's hydrogen. That's carbon, oxygen, hydrogen, carbon, hydrogen, hydrogen. CH3COOH. So this hydrogen right here would be attracted to a water molecule nearby, and so it will form, so that interaction between that hydrogen on that acetic acid molecule with the lone pair on the oxygen of a neighboring water molecule is what you would call a hydrogen bonding interaction between these two molecules. Okay? So that's capable of hydrogen bonding interaction there. Is there any other atom here that's capable of hydrogen bonding interaction? I'll give you another one. Okay. Remember your oxygen has two lone pairs, right? Well, what if there's a neighboring water molecule that has remember in a water molecule, your hydrogen is attached to an oxygen, right? So that can be a hydrogen bonding interaction right there. So to answer this question, how many atoms in this molecule are capable of hydrogen bonding interaction with water molecules? Is it 1, 2, 3, or 4? I've shown you 2 already, so it's not 1. Is it 2, 3, or 4? Alright, where's the other one? Here's another oxygen atom, so it's got 2 lone pairs, so that would be attracted to a water molecule by way of the water molecule's hydrogen. Anything else there that has a lone pair? That's it. CH3COOH is this structure right here. Okay, so this is capable of hydrogen bonding. This is capable of hydrogen bonding. This is capable of hydrogen bonding. 1, 2, 3. Which one? This one?
Yeah. Like the one on the top because.
Oh, I just drew it differently. Let me redraw it. The answer was 3, right? Okay. I just drew it. Okay, so the way this is shown right here, okay, that's C double bond O. I'm sorry, C O H, and that's the double bond O right there. See, that's a double bond right there. That's a single bond. Okay. The fact that this carbon has a steric number of 3, there's only 3 groups sticking out of it, tells you that one of these would have to be a double bond, and it's this one right here. Okay. So you have to review your molecular structure. Okay. What about these hydrogens right here? Why aren't they capable of hydrogen bonding? These are not capable of hydrogen bonding because the hydrogens are not attached to fluorine, oxygen, or nitrogen. They're attached to carbon. A carbon to hydrogen bond is a nonpolar bond, essentially nonpolar. Okay? So that hydrogen is not very attractive to an electron pair on a neighboring water molecule. So correct answer here is B. So how do you explain why O2 is a gas while water is a liquid at room temperature? What type of interactions do O2 molecules have for each other? Does it have dipole-dipole interaction? Let's compare a pair of oxygens versus a pair of water molecules. Dipole-dipole. Oxygen. It's nonpolar, right? Water molecules can have dipole-dipole. Hydrogen bonding. None. Water molecules can have hydrogen bonding interaction, right? What else? London dispersion forces. They both have London dispersion forces, but they're both small molecules. So the anomaly really here has to do with the hydrogen bonding. Yes. You would expect actually O2 is a little bit bigger than H2O. Okay, you would have expected stronger London dispersion forces, but water molecules have an unusually strong attractions for each other because of hydrogen bonding interaction.